While the ray model of light might be a bit simplified, it really helps us develop a conceptual understanding of how light reflects off of objects. But there's actually another optical phenomenon that can be just as intuitively understood using this ray model of light, and that is the phenomenon known as refraction, otherwise known as the bending of light. So let's take a bit of a tangent at first. Let's say that you are in some sort of environment here that's like a sandy bank, another sandy bank. And between these two banks, we have some sort of, let's say it's kind of like a creek or a stream or something that you don't have to swim through, but you're going to have to wade through to get from one side to the other. Now, if you wanted to get from where you are currently to this red X in the least amount of time, well, what's the path you would take? Well, you would take, obviously, just a straight line, because the shortest path between 2 points is this straight line. This would definitely be the way to get there the fastest. But what happens if we change that scenario up? Let's say now you're located up here, and where you want to go is this red X down here. Now, some people might instinctively just say, oh, well, you would just take that straight line, right? Because, once again, that's the shortest path. But I bet, if you think about it, this is not actually the path you would take to get there as quickly as possible. Because you know that when you're moving in this middle area, this stream that you have to wade through, you're going to be going slower than when you can move on the two banks. So you need to minimize the amount of time you're in the stream and maximize the amount of time that we're in the banks, at least to a degree. So a more likely way we're going to accomplish this is we're going to come in at this bank at a bit of an angle, and then you're going to cut more directly across the stream. Now, you may not go perfectly horizontally across, because you might be able to wade enough to go at an angle, and then you're going to, once you get to your B line, more directly for this red X. This would be the fastest route in this particular situation. But now let's apply what we just learned to an optical scenario. Let's say we have a block of some material, and this material could be plastic, glass could be filled with water, doesn't really matter. But the only thing that's important is that this material causes light to travel slower through it than it would in, let's say, a vacuum. So if we have a vacuum around this material, the light travels faster outside, slower inside. And if we emit a light ray from point A and it's going towards point B, we know that's where it's going to end up. What is the path it's going to take? Well, you might be able to instinctively realize it's just going to be a straight line. And well, why is that? Well, remember that light obeys Fermat's principle, the principle of least time, and it will always take the path that takes the least amount of time. And in this particular situation, well, the path that would take the least amount of time would just be this straight line. So this is one particular, the angle of incidence is 0 degrees. I know I put a 90 degrees here, but that's just supposed to remind you that this light beam is basically striking normal to the surface, parallel to the optical axis of this block. But let's say the light beam was coming in at an angle and going to point B. What would be the path that the light takes now? Well, once again, the light obeys Fermat's principle. It takes the path that takes the least amount of time. And if that is the case, the light is going to come in at an angle here, and this angle will be some angle between 0 degrees and 90 degrees, the angle of incidence. And then when it gets to this surface, it's going to go more directly through the material, because it goes slower through that material, and then it's going to go take a more direct route from this point, because it can go faster from there. Now, once again, remember that although this is the path that takes the least amount of time, the light can't physically understand how it does this. It doesn't have a brain, and we will learn more about why it does this, particularly when we get more to waves. Right now, let's just focus on the phenomenon we're observing itself. So this was an example of the phenomenon known as refraction. Refraction is the change in direction or bending of a light ray as it's transmitted from one medium to another. So for instance, when this light ray comes in, it comes in at an angle. It's going to take a more direct route. It bends as it goes from one medium to another. And then when it gets here, it's going to bend again as it goes from this medium of the block to leaving that medium. Now, a very key point here, though, is that this only happens at a non-perpendicular angle. If the light was to come straight in, it would just go straight through. But that is not the case here. Okay, now why exactly does this occur? Now, we already kind of talked about this a second ago, but really it all has to do with the fact that the speed of light is reduced in certain media. It's not going to be traveling at 3 × 10⁸ meters per second, and since it goes at different speeds in different media, that's going to cause it to take different routes. Now, typically speaking, what is the speed of light in certain materials? We remember that light is really an electromagnetic wave, and so it's going to interact with the electric charges in these materials. You have particles that are closer together, typically speaking, that means that the light is going to be more affected by more charges and therefore is going to travel slower. Now, that's not 100% the case. It has to do with things like charge distribution. So it's not just a correlation with density. In fact, we often call this something known as optical density, and some materials are more optically dense than others, but typically solids are more optically dense than liquids, which are more optically dense than gases. Well, how do we specifically categorize materials by the speed of light in them? In other words, if I look at two materials, what property do I have to specifically have written down somewhere to know, okay, the speed of light is faster in this material than in this material? And that is something known as the index of refraction, that we abbreviate with a lowercase n. And n is equal to c over v, where n is the index of refraction for some particular material, c is the speed of light in a vacuum, so that's 3 times 10 to the 8th meters per second, and v is the speed of light in that particular material, meters per second. Now notice, because we have meters per second over meters per second, this means that the index of refraction is actually a unitless number. It's just going to be some value. But what are some other things we can notice about the index of refraction? Well, first, it will never be smaller than 1. Because the only way we could get a fraction less than 1 here would be if the speed of light in this particular material was greater than the speed of light in a vacuum, and that is not possible. So the lowest index of refraction we can get is actually that of a vacuum, which is equal to 1, because it would be 3 times 10 to the 8th meters per second divided by 3 times 10 to the 8th meters per second. Alright, so if we have a bigger n, if we get a bigger value here, what that is telling us is that the material is more optically dense and that the speed of light in that material is slower. On the flip side, if we get a smaller n, a smaller index of refraction, that means it is a less optically dense material and the speed of light will be faster through that material. Now, if we look over here, for instance, we can see that, for instance, diamond has a very big n. Light travels slowly in diamond compared to, for instance, glass, which travels slowly compared to water, which travels slowly compared to air. And this is one point we really want to highlight, is that the index of refraction of air is very, very close to that of a vacuum. Instead of being 1, it is 1.0003, and we always, whenever we're doing calculations, unless you're doing something very, very, very precise, we just say, okay, the index of refraction for air is 1. That's a number, though, that we will probably want to make sure that we have down. So once again, let's say we have a block, and we'll go and say that this block is made of glass and it's placed in a room filled with air. And we have a light ray coming in at a non-perpendicular angle. Alright, well, when the light ray hits the block, it's going from one medium to another, and there's 3 things it can do. Some of the energy will be absorbed in the glass, it will warm up slightly. Some of the energy will be reflected, and additionally, some of it will be transmitted and refracted through the glass because it's moving from one medium to another. But how can we mathematically analyze this? Well, first, let's make a quick note that if we look at the normal line here, this theta 1 would be my angle of incidence, and that's going to be equal to the angle of reflection for this reflected light ray, so that's theta 1 and theta 1. But I don't really care about the angle of reflection right now. We're trying to understand how does it refract. So I want to look at this theta 2 for the refracted ray. And notice it is once again defined with respect to the normal, but theta 1 and theta 2 are not equal to each other. So how can we relate the two? Well, we do it through something known as Snell's law. And Snell's law, you can just think of it as the law of refraction, just like we had the law of reflection. And Snell's law is n1 sine theta 1 is equal to n2 sine theta 2, where n1 and n2 are the indices of refraction for the two respective media we have here. So in this particular situation, I would say the index of refraction n1 would be the index of refraction of air, n2 would be the index of refraction of this particular glass. Theta 1 is the angle with respect to the normal of this incident ray, and theta 2 would be the angle with respect to the normal of this refracted ray. Though if you notice, we could flip these two, it doesn't really matter, but we want to make sure that we have everything on the refracting side on one side, everything on the incident side on the other side. So let's go ahead and say in this particular scenario, we knew that the index of refraction of air is 1, and let's say for this particular glass, the index of refraction is about 1.6, and that the incident ray, or theta 1, is coming in at a 30-degree angle with respect to the normal line. And let's go ahead and figure out theta 2, the angle with respect to the normal for the refracted ray. Alright, so I've got n1 sine theta 1 is equal to n2 sine theta 2. And I'm going to go ahead and just rewrite that so I don't get confused with my 1s and 2s. I'm going to say n of the air sine theta of the air is equal to n of the glass sine theta of the glass. So I keep them separated away from each other. And we're solving for theta of the glass. So to find that, what we're going to have to do is I'm going to divide both sides by n sub g. And then I'm going to take the arc sine, or the inverse sine function, sine to the minus 1. And if I do that, I have sine to the minus 1 of 1 times the sine of 30 degrees over 1.6, pull my calculator out, plug that in, and you get an angle of about 18.2 degrees. So this theta 2 going through the glass with respect to the normal would be 18.2 degrees. But this light ray is going to continue on this straight line until it hits the other end of the block. But at that point, it is going to refract again at this boundary between the glass and the air. Now, first off, what is this angle of incidence, or the incoming ray? Well, that's going to be at 18.2 degrees, because these are alternate interior angles, so they're going to be exactly the same. So I want to know what's going to happen beyond this point. So I'm once again going to use Snell's law, and I'm basically going to just do it in the other direction. I'm going to say I'm solving for theta of the air rather than theta of the glass. So I'm going to have sine to the minus 1 of 1.6 times sine of 18.2 degrees. I have to put this new angle in, divide by 1, and when I do that, I actually end up with 30 degrees. So the angle that it was actually traveling in here is actually the angle it goes out here. But the difference, though, it doesn't go in a straight line. It's been essentially shifted from one side to the other. But the thing is, though, this problem's actually already introduced us to 3 big trends that we want to make sure we have down. 1. When the light goes from a material with a lower to a higher index of refraction, so when the second material has a bigger n, light will always bend toward the normal. So coming in here, that's going in at 30 degrees. It goes to a material with a higher index of refraction from air to glass, so it literally bends towards that normal line. Now, 2 is kind of the flip of this. When we go from a material with a higher index of refraction to a lower index of refraction, for instance, going from glass to air, it bends away from the normal rather than toward the normal. We want to make sure we have this down. This is pretty crucial. All right, and then the third one is kind of just a point that is good to know, which is that if we're returning to the same medium on one side of the object and the other, it's actually going to go out at that same angle as long as those two surfaces are parallel to each other. If this is some sort of weird shape, we would not be able to say that. We would have to find a new normal line and recalculate. But for this particular situation, that worked out okay. So let's do a practice problem. Let's say we had like a pool of water, and water has an index of refraction of 1.33, and we are pointing a laser pointer down at it at a 70-degree angle with respect to this normal. So a laser pointer light is going in, and it's going to strike the water right here. And the question is, at what angle is this beam going to refract? Well, before we even solve for it, I want you to first think, okay, is it going to bend toward the normal or away from the normal? Well, we're going from air to water, so we're going to a higher index of refraction, so it should bend toward the normal. Our angle on the other side should be smaller than 70 degrees. Now go ahead, pause the video, try this out yourself. Let's see how you do. All right, well, hopefully you gave it a shot, and if you go ahead and just use Snell's law, and you rearrange it in terms of theta of the water, we will end up getting an angle of refraction, or a theta 2, of 45 degrees, which matches what we predicted. But let's go ahead and kind of flip the scenario. Let's say you were like underneath this pool of water, you're like in a swimming pool and you have a laser pointer, and you shoot that laser pointer out of the water at a 70-degree angle with respect to this normal. So we're doing it upward from beneath the water rather than down to the water. And let's go ahead and do this again. Now, we can already instinctively say that the angle should be bent away from the normal because we're going from a material with a higher to a lower index of refraction, but go ahead and try to calculate it now. All right, you might have gotten a little frustrated there, because if you start sticking numbers in and we solve for theta of the air, well, you start sticking in our numbers and we get 1.33 sine times 70 degrees over 1, that comes out to be 1.25, and you try to take the inverse sine of 1.25 and your calculator won't do it. Well, why won't it do it? Well, we can't take an inverse sine of any value greater than 1, so we're getting an apparently impossible value here. So what is going on? Why can't we figure out this angle of refraction? So let's think through this a little bit. Let's say we have a light beam going from a material with a higher index of refraction, so N1 is higher, to a lower index of refraction, just like we did with the water and the air. Well, if that light beam goes straight up through the material, well, there's no angle of incidence, there's going to be no angle of refraction, it's just going to go in a straight line. Now, some of this light will reflect straight backward, but a lot of it is going to be transferred from one material to the other. All right, so let's complicate a little bit. Let's say we start to come in at more of an angle. When we come in at more at an angle, some of it will be reflected, but not very much, but we're going to have a lot of it refracted, and it's going to bend away from the normal because we're going from a higher to a lower index of refraction. Okay, this makes sense so far. Let's take this even further. And when we take it even further, more of this beam is going to be reflected, and it's going to be refracted to an even greater angle. It's going to be bent even further away. All right, still making sense? But let's go to this next situation. If we make this angle big enough, a lot of it will be reflected, and this beam is going to be refracted so far, it is literally going to ride the surface of this material. Instead of going up at an angle, it's just going to go directly this direction. And this is known as the critical angle here, often abbreviated as theta c. And when this occurs, the refracting light ray basically gets trapped along the surface. So your theta 2, your refracting angle, is equal to 90 degrees because it's 90 degrees away from that normal line. But if we take it even further, so that our new incoming angle here, our incident angle, is greater than the critical angle, it's not even going to be able to refract along the surface. It's going to bend so far that it no longer refracts at all. In fact, all of the light beam at this point, when this incoming angle is bigger than the critical angle, will be reflected. None of it will be refracted. And this is a phenomenon known as total internal reflection. So let's go ahead and read the definition and talk about specifically what it means. Total internal reflection is an optical phenomenon in which a light ray being transmitted from a material with a higher index of refraction to a material with a lower index of refraction at an angle beyond the critical angle with respect to the normal results in the entire ray being reflected back into the original material. So looking at this picture here, we have this going into the straight line here, but it hits this at a grain of, this is apparently beyond the critical angle, because none of it is refracted out, it's not bent this way, it all is reflected straight down within the same material. Now it leaves here because it's seen at a nice perpendicular angle. Okay, so what exactly is the value for this critical angle theta c? Well, if we use Snell's law, n1 sine theta 1 is equal to n2 sine theta 2, well, we're going to replace theta 1 with this critical angle. If we go beyond that angle, we are not going to have any refraction. And even at that angle, it's just riding along the surface. And remember, when it's riding along the surface, theta 2, or the refracted ray, is at a 90 degree angle. But sine of 90 degrees, that's just 1. So now if I want to rearrange this a little bit, I can say, oh, okay, I divide both sides by n1, and I'm left with the critical angle is equal to the inverse sine of n2 over n1. And in fact, this is the equation for the critical angle, where the critical angle is, we'll go ahead and do it in degrees, but it is the inverse sine of n2, which is the or the index of refraction of the material that the light ray is entering into, divided by n1, the index of refraction of the material the light ray is leaving. So in this particular scenario, let's say this was made of acrylic, then n1 would be the index of refraction of acrylic, and then n2, if this is just air out here, would be the index of refraction of air, or 1. So n1, what you're leaving, n2, what you're entering. But remember, and I didn't really talk about this yet, but this is a very important point, is that this only works when n1 is greater than n2. It only works when we're going from a material with a higher index of refraction to a material with a lower index of refraction. It will not work the other way. That's the only time we're going to experience total internal reflection. So let's go back to this previous problem where we tried to shoot the light ray up at the 70 degree angle, and let's see if that's even possible, because it seems like it's not. So let's go and figure out what is the critical angle for the light ray going from water to air, and therefore will this beam refract or reflect? And you can probably already guess what's going to happen. But let's go ahead and plug in. So we're going to do sine of theta 1, where n2 is going to be the index of refraction of the air, and 1 will be the index of refraction of the water. We stick those in, you get an angle of about almost 50 degrees, 48.8 degrees. So anything beyond that angle will be totally internally reflected. So what is this light beam going to do? definitely going to reflect. None of it is going to be able to escape the surface of the water. It's just going to reflect back into it. So what are our main takeaways on this lesson of refraction? Well, one, can we describe what refraction is? This bending of the light rays as they move from one medium to another. Explain what causes it, which is the fact that light travels at different speeds in different mediums, and utilize trends that light rays follow when refraction occurs. Most importantly, the light rays going from a higher index to a lower index bend away from the normal, and light rays going from a lower index to a higher index bend toward the normal. You got to get that straight. Can we calculate the index of refraction for a given material using the equation n is equal to c over v? Can we utilize Snell's law, n1 sine theta 1 is equal to n2 sine theta 2, to determine how specifically an incoming light ray will refract through a material? And lastly, can we describe why and how total internal reflection occurs and calculate the critical angle for which that will occur, keeping in mind that that will only happen when we're going from a material with a higher index of refraction to a lower index of refraction.